This time we're going to find the volume of a solid by revolution, and we're going to use the disk method. The question is saying, find the volume generated by rotating the region bounded by y equals 1/4 x squared and y equals 5 minus x squared about the line y equals 7. So right off the bat, the best way to attack any volume question, give yourself a good sketch. Sketch out what the graph of this might look like. And now, you should be familiar enough with functions to know that 1/4 x squared, that is a parabola facing up, and it's kind of wide. It's been flattened a little bit. And then 5 minus x squared, well, that negative x squared means it's a parabola facing down, and the 5 means it's been shifted up 5. So it's something sketched like that. You should be able to give a rough sketch like that, enough to know that they intersect twice here. We've got a region enclosed there. So really, a rough sketch like that is enough to solve this integral, find this volume. Now I did go ahead and create the very nice looking graph over here to give us a real good idea of what's happening. So we are asked to find the volume of this region enclosed here when it is rotated about y equals 7. So my axis of rotation is going along right here. So you kind of think, visualize, what is this going to look like? Well, it's going to, when it rotates fully around, you have something like that. Pretty rough sketch. And it's doing the 360 rotation, so it's coming around like that, and it's coming around that way. But the big thing to focus on is you got your other image up here, and I need to find that volume of revolution. So it appears that I have a hole in the middle of my solid right here. I've got a hole, which means I'm going to be using this method, but the specific version of it, the washer method, because each of my washers is bouncing from this top function to this function, and then the corresponding one would be up here. Imagine that little rectangle revolving around the line y equals 7, and in the middle you're going to have this as a gap. This is the hole. That's the hole in your washer. And we also can see that as we fill up this volume, we are going to be moving along the x-axis to fill it up. If we start right here and move on over this way, our rectangles are going to continue to fill up our volume, or I should be more specific, our washers are going to fill it up. So if we look at this sideways and consider what the cross section of our washer would look like, we'd have the outer, and then we'd have the inner, and there's that hole in the inside. So the question becomes, what is the area of each of these washers? Because then we'd find the area of one of those washers, and we multiply it by however many washers fit inside that volume. Or to get the exact, that would be an estimate, but to get the exact, we use calculus and we use integrals. So we multiply by our width dx. Let me write out what the general volume integral is. So volume is equal to pi times the integral from a to b of, remember this is a radius now, or sorry, a washer, so we have our outer radius squared minus our inner radius squared dx. Y radius squared, outer minus inner, well, we think the area of this cross section right here is a circle, so the area of it is pi r squared, and then the outer minus inner, I find the area of this bigger square, pi r squared, minus the inner area of the inner circle, and I am left with the in-between area, and that's what I want. And now I multiply by dx because it fills up my solid. Okay, why did I choose dx? I chose dx because I'm using the washer method, and my axis of rotation, this guy right here at y equals 7, that axis of rotation is horizontal. Whenever I'm using the washer method and I have a horizontal axis of rotation, I'm going to use dx, which means all my functions are going to be in terms of x, because I got to match up my dx with my what my function is in. If I was rotating about, for example, the line x equals 5, now that's a vertical line, which means that the integral is going to have dy, and I need to get all my functions in terms of y. So it'd be like x equals y squared or something like that. But I have a vertical line, or so I have a horizontal axis of rotation, so I'm going dx. So here's my general formula for my volume. I need to now set up my outer radius and inner radius. What are those? So radius outer is equal to radius inner is equal to. Okay, I'm going to clear up our graph here so that we can see again. So our axis of rotation right here at y equals 7. One of my radiuses going from here to here, that would be the inner radius. Going from our axis of rotation all the way out here, that would be our outer radius. So imagining on the circle over here, starting here, this is going to my inner radius, and this is going to the outer radius. Alright, take another look over here, going at the inner radius. I'm going from my line to what function? What is the inner radius? Well, it's this upside down parabola. And what is that graph? It's y equals 5 minus x squared. So somewhere in my inner radius, I'm going to have 5 minus x squared. And then my outer radius, well, that's going from here to here. What is this facing upwards parabola? That's the 1/4 x squared. So the outer radius is going to have 1/4 x squared in there somewhere. Now why isn't it just 1/4 x squared? Why isn't it just 5 minus x squared? Well, we would have that if it was rotating about the x-axis, or if we were rotating about the y-axis and going in respect to dy. That makes it really simple. Then your inner and outer radiuses are just the functions themselves. However, since we are rotating about y equals 7, it changes things. But not too much. It is only, turns out to be 7 minus 1/4 x squared, 7 minus 1/4 5 minus x squared, or possibly 7 plus 7 plus. So your axis of rotation affects that. And I like to play around with things to see how I can get my radii to match up correctly. So if I'm right here, I'm at the spot x equals 0. What should be my inner radius? Well, I can easily count this. It should be 2. So if I go over to my inner radius, whenever x is 0, my inner radius should be 2, because it has a length of 2. Well, 7 minus 5 minus 0 squared is equal to 7 minus 5, equal to 2. Okay, check. It works out. The inner radius has a length of 2. Well, what if I go over to the edge of my solid at x equals 2? What is the length of the radius then? 1, 2, 3, 4, 5, 6. So now, when I plug an x equal 2 in, I should have a radius length of 6. 7 minus 5 minus 2 squared is equal to 7 minus 5 minus 4, which is 1. 7 minus 1 is 6. Okay, good. Both of my radiuses check out. And I could do the same with the outer radius. When x equals 0, my outer radius is 7. That full length there. 7 minus 1/4 times 0 is 7. Good. What about when I'm at x equals 2? Radius here is also 6. 7 minus 1/4 times 4, which is 1. 7 minus 1 is 6. Hey, good. The formulas, the equations we have come up with for our radius, they work. There's actually a kind of general rule that you can apply to when you're trying to set up your radiuses, or your radii, I suppose I should say, because it can be confusing. Should I go 7 plus 1/4 x squared? Should I go 1/4 x squared minus 7? 1/4 x squared plus 7? Just 1/4 x squared? If your axis of rotation is above or to the right of your volume, then your radii is going to be the absolute value of c minus f of x. So c, that's the axis of rotation. So in this case, it's 7. So it's the absolute value of c minus f of x. If the axis of rotation is below or to the left, absolute value of c plus f of x. And that's a general principle. I would still set up your radius and check it out. Just try out a few values. If you have 0 in there, try that out, and then the boundary point or the end point of your volume, check that out and see is the radius equal. But I did find that this general principle works for setting up your radii and picking should it be minus or plus, on which side of the function. Okay. So we have our outer radius and our inner radius. Good. Next step is to set up the integral. As we have pointed out up here, we are going to have volume is equal to pi times the integral from a to b. Wait a second, what's a and b? Well, that's the endpoints of our integration, which means our solid goes from where to where. Well, we have it graphed nicely so we can see it goes from here to here. What are those x values? The way you want to solve for your x values is by taking your functions and setting them equal to each other. Because where do those functions intersect? Where are the boundary points of our region? Where the two functions intersect. So you take your original functions, 1/4 x squared and 5 minus x squared, and you see where they intersect. So 1/4 x squared is equal to 5 minus x squared. I'll add that x squared over, and I get 5/4 x squared equals 5. Multiply by 4. Those cancel out, so it's 5x squared equals 20. Divide by 5. X squared equals 4. Take the square root and you have x equals plus or minus the square root of 4, which is plus or minus 2. That tells us the boundary points of this region occur at x equals -2 and x equals +2. Therefore, the bounds of integration, it goes from -2 to 2. Alright, then it's times the outer radius squared. So it's 7 minus 1/4 x squared squared. Remember that it is tempting to just do radius outer, but it's your radius squared minus your inner radius squared. And that again comes from the area formula for a circle, pi r squared. Inner radius squared, 2 plus x squared. That's because our inner radius, it's minus 5 and then minus a negative x squared. dx for our integration. Okay, so then you take that integral, and the answer to that will be your answer to your volume. How much volume does your solid take up? Now, the hard part in these volume problems is the setting up the integral. Often once you set up the integral, it's fairly easy integration to complete. This one is slightly annoying as we have to FOIL twice and there's fractions involved. So actually I went ahead and solved it, and we're just going to take a quick glance through some of the work. So again, this right here is the work for that integral. Up top, we have the same integral just rewritten again. I had to, going on this step, foiled. So I foiled both of them, and then going on to my third step, I combined like terms. Once I had it combined, it's just using the power rule, a whole bunch for integration, and then I had to evaluate at 2 and negative 2 like here, and then just combining some like terms. And finally, pi times 64 minus a negative 64 is pi times 128, which means the volume of my solid is 128 pi units cubed. And that right there is the final volume. Again, the hardest part is setting it up, but once you get it set up, once you identify that you're using the washer method, you have rotation about a horizontal line, therefore it's going to be dx and everything in terms of x. Find your outer radius, your inner radius, put together the integral and solve.